routing purposes. So the lecture outline will be regarding interior and exterior routing. We will start with the RIP, and after that we will look at OSPF and BGP in the second part of this seventh lecture. So let's start from the introduction. You know that internet is a combination of different networks, and this network should be connected through routers or any other devices. But mostly there are routers which connect different type of networks. So the major thing in the network is basically how can you pass a packet from the source to destination using the available pathways, and which path should be followed. So you know that there are different paths that a device can have towards its destination, but which path to follow is the basic thing, and this is known as basically routing. So this routing basically depends on the metric. Metric is basically a cost assigned to a device that is used, or that is paid for passing through the network. If you are passing through a device, so you should bear some cost. Either it is the hops, or it is the time, or it is anything that you expends spent on the on your way towards your destination is basically known as a metric. So a router should choose the route with the smallest metric. If the metric is, let's say, number of hops, so a router should be able to choose minimum number of hops. If the metric is basically you do not care about the number of hops, you want your data to reach the destination with the minimum number of time, minimum time. So the metric should be time. So metric depends upon the routing protocol. So the metric assigned to each network depends on the type of the protocol, which type of protocol you want to use, and with along with that you have to bear that cost. Let's say this RIP, that is routing information protocol, commonly known as RIP. This treats each network as equal, and the cost is basically the hop. In RIP, that is routing information protocol, the cost that you the metric is basically the hop count, that which hop from a transmitter towards a receiver. Let's say you have multiple paths. One path is this is your receiver, so you can see that, let's say, 1 2 3 4 5 and 6, there are 6 hops towards the destination. And there is another path which is this. Let's say there is only one hop, 1 and 2 hops, let's say. The second path is most optimum as compared to the first path if you are using this protocol, because this protocol takes a metric as a hop count. So for this, if you are using this kind of protocol, we will discuss more about this protocol in the coming slides as well. But for just for introduction, you should know that this protocol basically uh, take the hop count as a metric. The other option that you can have is basically OSPF, that is open shortest path first, and it is also a very good protocol. And you know that you should know that this to assign it allows the administrator to assign a cost for passing through the network based on the type of service. So for example, you can you want if you want to have maximum throughput or minimum delay. So these are some parameters, or you can say metrics, that you consider while you are using OSPF, and it is mostly used nowadays because of its different matrices that it provides. And we will discuss that in the second part of this lecture in very much detail. And the last one is basically border gateway protocol. This is also a kind of protocol which supports this kind of protocol, because these both are some kind of different. That is why I've placed this topic in another lecture. So we will confine ourselves to this protocol for today's class. So a routing table can be static or dynamic. So I have already discussed some kind of static and dynamic protocols, routing methodologies with you in the previous class. That was lecture 6A basically. The first part of the sixth lecture, we studied that there are two types of routing protocols. One is static and another is dynamic. Dynamic means internet should have the net router should be able to revisit and count the cost or the metrics periodically. And static is some kind of that information that is stored by force in the router. So there are two kinds of routing. But the first one is static, the second one is dynamic. And internet needs a dynamic routing table, means the internet should be able, or the network should be able to revisit or recount their matrices, so that the periodic table, or sorry, the routing table, not the periodic table, it's the routing table. The routing table should be updated version, not the any version that consists of some devices which are not in the network after that. So dynamic routing table is achieved by the routing protocol. So how can you achieve this routing protocol? Let's start with the some basic terminologies, that is interior and exterior routing. So what is this interior and exterior routing? So an internet that is an internet can be so large that one routing protocol cannot handle the task. You know that mostly the networks are much larger. I am talking about the internet. So one routing protocol or one routing table is not enough to manage all the routers that is in the path between the transmitter towards the receiver. So for that you should have an ability to divide your network, to divide your internet into different sub networks. So we call this different sub networks basically autonomous system, AS. So AS is a group of networks and routers under the authority of a single administration. Consider the example of your university. Our campus is basically managed by a single administrator, but all of these network is basically divided into sub other networks. There are, let's suppose, 5 or 4 other networks as well. We also discussed this in the course topic for the subnetting, but you know that all these subnets are basically controlled by a single administration, by a single authority. So these are basically autonomous system 1, autonomous system 2, AS3 and AS4, and this is your single administrator SA. So interior routing and exterior routing. Interior routing is that routing which is basically inside an autonomous system. You see that if you are using some kind of networking inside one AS, inside this one AS, this is basically known as interior. And if you are using some kind of routing that is basically connecting two different autonomous bodies, let's say one is want to communicate something to 4, so this is basically known as exterior routing. And interior routing basically is RIP and OSPF and the examples, and the exterior routing basically is BGP, border gateway protocol. We will discuss that all of these in different terms and technologies later on, but for this time just keep in mind that these are two basic divisions, classifications of this routing protocols, and the first one is RIP, the second one is OSPF. These both are basically interior used for interior routing, that is inside our autonomous body or inside our autonomous system. And if you have more than one autonomous system and you want to communicate different through different autonomous system, let's say this is your 1, this is your 2 and this is your 3, and 2 wants to send something to 3, so that is where you can use this exterior routing protocol. So example, you can see that in the following example, in this example, this R1, R2, R3 and R4 are basically use an interior and exterior routing protocols. You can see that the solid lines are basically the ones that is basically, you see that the solid lines are interior routing protocols, and the broken lines, thick lines, are basically showing the exterior routing protocols. So you can see that this is basically interior, this is basically interior, this is interior, and these are basically exterior routing protocols. These are basically exterior routing protocols. All the solid lines are basically the interior routing protocols, and these are the black ones is basically showing the devices or the nodes or terminals, anything you want to call it, and the red ones are basically the routers. These are the routers, they are different routers. So this R1 is the gateway, or the you can also call it gateway of this autonomous body. This R2 is the gateway of this autonomous body. This R3 is basically the gateway of this body, and this R4 is basically the gateway of this autonomous body. So coming towards our main topic, that is the routing information protocol. This routing information protocol is based on distant vector routing. I hope that you have learned about the this kind of terminology. Even not even if you are not learned, you've not learned. Maybe I will assume that you have at least listened about it. So it is based on basically Bellum-Ford algorithm, and we will talk about this algorithm later on. And it is used for calculating the routing tables. So what is distance vector routing? Each router periodically shares its knowledge about the entire internet with its neighbors. So let's say you have a kind of something like this. This is your device one. These are not the networks. These are just devices. This is device two. This is device three. Similarly, you have a big network. This is device four. So you can see that neighbors of one is basically one, and these are connected to something like this. And this is, let's say, this is the 5. So each device will be communicating its or telling its periodic table or its knowledge to the every of its neighbors. So one will tell everything it knows about the 4 and 2 and 3 to these three. 3 doesn't know about 4. Similarly, 2 this one doesn't know about 5. So 2 will tell the one that I have connected through the 5 using one hop. So all these devices will be telling each other, will be sharing its information of all the network that they knew till now to each other. So this sharing of knowledge about the entire autonomous system, at the start router's knowledge may be sparse. They do not have that much knowledge, but after some time it will be something that will be of great importance. So after some time one will exactly know that where is 5, because of the periodically upgrading or updating of the routing information that is provided by 2 to 1. Similarly, sharing only with the neighbors is the only thing that you want, because you don't this, let's say this is 1, so one doesn't know about 5. So how does it will send the information towards 5, because it hasn't heard about 5 till yet. So it will ask 2 that please tell me what information do you have about any other devices. So 2 will reply that I have another device that is 5 and it is connected to me directly in a single hop. So that's how one will know about 5. So it will keep updating its table, and it basically occurs in after regular intervals, or you can say periodically. This process is periodic. So this is basically known as distance vector routing. You know about the devices that are at distance from you using a periodically upgrading or updation of the neighbors as well. So coming towards our this protocol, this is basically that routing information protocol, commonly known as RIP, and it is a kind of upgrading information or updating information. A routing table is basically this is the you can say the pseudocode, or you can say the algorithm that is done by, or that is accomplished by this protocol. A routing table is updated on the receipt of RIP response message. This receipt is basically a response message, and it adds one hop to the hop count for each advertised destination. So I will tell you in the detail in the coming slides as well. You just have to count the hops. Actually, I have already told you that this information or this protocol is just regarding the ones of the hop counts. So after every upgrading or updating of the information or routing table, it basically adds the hops or subtracts the hops as well. If the device is now not in the network, it will remove it as well. So repeat the following steps for each advertised destination. Let's say if a destination is not in the routing table, this is a router R1, let's say, and this is your device, let's say A wants to send something to B, but B is not in the information table or the routing table information of this router. So this will be add the advertised information to the table. So B, this R1 basically add B in the routing table, and it will ask its neighbors to please share the information regarding B. Else, if it has the information about B, it will just replace the entry in the table with the advertised one. So it will just replace the entry that okay, I have got another entry or request for B. So it will update its routing table based upon their information that is provided inside the table. So if the next hop field is the same, it will replace the retry in the table and will advertise one, or else if the advertised hop count is smaller than one, so it will replace the entry into the routing table. Let's say a this R1 has no has the information about B, and it know that B is at let's say 4 hops to me. But after the information that is, because you know that this is periodic updation or upgradation, so after some time R1 know that B is now at 2 hops to me. So if another time A wants to send something to B, so it will ask the router R1. Now router R1 now know that B is not at 4, it is now at 2. So it will first look at inside the table, and if it is B is equal to 4, if not, if let's say the first case that B is not present over there, so the first thing that it will do is it will enter the information about B, that B is equal to 4, B is equal to 2, because it know that now there is 2. Let's say the second case, B has the information of this R1 has the information regarding B, and it know that it has mentioned information about 4 hops. But now R1 know about the due to the process of updating, R1 know that B is now at 2 hops, so it will replace this, delete this entry, and instead of 4 it will add 2 to the entry. So this process will go and again keep going, because the more it takes time periodically of updating, it will give you the good value. Not in the very start, it will take some time to get stable, and we will discuss that the stability of this protocol as well in the coming slides. So this is the same protocol, and this is the example of the updating of routing table. So you can see that this RIP message is from C, and this RIP message from C after the increment. So 4 becomes 5, 8 becomes 9, this 4 becomes 5, this 3 becomes 4, and this 5 becomes 6, and it will update the table. Now the new, this was the old routing table. Let me tell you, this was the old routing table, and the network there was 7 hops from A to the network 1. From C to network 2 there were 2 hops. From F to network 6 there were 8 hops. From E to network 8 there were 4 hops, and from F to network 9 there were 4 hops as well. So now based upon this information, this new information, it will upgrade. If the first information is a good one, so it will remove it, or otherwise it will keep up the old information. So you can see that from A to network 1 there were 7, and this is only for C. So it will we will just have to focus on C. So C is basically connected to the second network with 2 hops, and the new routing table tells me that C is basically connected to the network 2 using 5 hops. So this is the new information. Similarly, C is connected to the network 3 at 9 hops, because it is mentioned C is connected to the network 3 using 9 hops. Similarly, C is connected to user network 6 using 5 hops. So this information is basically updated, because you see that there was no information about C to network 1, 6, 8, 9. So there was information, we have to add. Let me change the color. So there was information about network C to 2 only, network 2 only, but there was no information about C to network 1, about C to network 3, 6 and 8. So it had the information about 2. So it will just replace the entry of network 2, and it will add the entry of these things as well in the table. So this basically this is the you can say the output messages in the tabular form, in the descriptive form actually. Network 1 no news, do not change. Network 2 same, next hop, replace. Network 3 a new router, you can see that it has added different router, it will replace that, do not change and do not change. So this is basically the procedure that is followed in this kind of protocol. The second thing is basically initializing a routing table. How can you initialize a routing table? So a routing table basically is activated using a configuration file. So the first thing that you want to have on any router is basically a configuration file. You know that this file is very important, and this file is basically varied from device to device or router to router. You cannot use one configuration file for all the different routers or the different protocols. So a router basically supports a single or some kind of configuration file. It do not supports all kind of configuration files, and similarly the routers can support some kind of routing protocols. So when a router is added to a network, it initializes a routing table for itself using its configuration files, and the table contains only the directly attached networks and the hop count that I am connected to. The hop count is basically 1 at the initial. It do not takes into account some other devices that are further and at hop 2 or hop 3. It will first add all those devices which is connected to itself using single hop or directly. So this is the first thing that every router do. After that, this updating of the routing table actually is achieved using the same procedure that we just saw. This procedure. So this is the initial routing in a small autonomous system, AS systems. You see that all these 14, 78 and 23 is basically the first thing that it will entry. And similarly this B will add 14 and 55 at the very start. Similarly this C will add 55 and 66 at the very start. And this D will add the 66 and this 8 at the very start, and this E will basically add 23 and 8 at the start of it, and this F will be adding 78 and 92 at the start of. You see that these are all basically single hops, one hop, one hop, one hop. These are the metrics in which we are dealing with in this kind of protocol, routing information protocol, single hop. This is the basic start, and after this some time, this is the final routing table for the previous figure. So after some time of after every router receives some kind of upgrading or updation information, this is the final information that every router will have. So router A basically know about the device, let's say B or E and F as well. It doesn't know about the C currently. Similarly, this router E will have the information about A, D, and A, and these devices as well, these networks as well. That this E will know that if I want to go to the 14, I have to follow A, because A is providing me only two paths. So if this has a packet for the network 14, it will know that I should go to A. So this router will forward the packet to this router, and this router is directly connected to this router. So there are two hops, 1 and 2. Similarly, there are other routing tables for this is for D, this is for C, and this is for B, and this table is for F. So you can see in this diagram, as let me clear the image and you will have something. You should notice something, that F is basically not connected to any of this router directly. F is just connected to this A. So that is why all the data from this this network or this network should be going to this network A. You can see that this is the only table in which all these are A, because F doesn't have any other path. So that is why all the entries using one hop, using two hops, or using three hops are provided using this router A, because F has no other option. It has to forward its packet to this A if it wants to communicate with any other network. So this is a kind of routing information. So let's talk about something inside this message protocol, is this routing information protocol message format. So the command bit is basically 8-bit, and this is two kind of information. This is one is request, or other one is response. If you want to request some information, you can put the field command 1, and if you want to want a response, you are transmitting some response to some information request, you are basically putting the command bit add response, and the value should be 2. Similarly, there is a version. There are 3 versions, and we will discuss that in the coming slides as well. It defines the version of RAV protocol. There are the family of 16 bits, and the TCP/IP value should be 2. The address basically is of 14 bytes, and the distance the hop count is basically has given the place up to 32 bit. You can have up to 32 bits of hop counts. So this is basically the protocol that you can see. This is the command, this is the version, this is the result for any other application you want to add in. These are all zeros, these are family, which family does it belong, network address, all zeros and distance. This is basically the same repeated things that we have discussed in this slide actually. So there are two kinds of basically messages. The first one is request, the second one is response. This request is basically something when a router wants to have some information about the entry, so it will send the request, and it can ask specific entries or all the entries. If you want to know about some specific entries, it can ask a request from that different router, or if it wants the information of all the routers to a specific router or device, it can ask that router about of its all information. So that router will provide it all of entries to this router as a response. So this is the response. This is a request to single one or multiple, and this is request to all. If you want to request all of the networks, so you have to put all zeros actually. I've already told you about the concept of all zeros and all ones, so that will be applied over here as well. And response is basically something that is sent after you receive a request. So that is basically a response packet. So here there is some kind of examples given to you, and it is asked us which is the what is the periodic response sent by the router R1 in the next slide, and assume that R1 knows about the whole autonomous system. So this is the example, and this is the solution as well. So I have given the solution to you as well. Just you just have to visit it once, and if anyone is that much capable to understand this example, I will also explain this example in the class as well. But if anyone wants to if anyone have explained it to me in the class, he will get a +1 as a bonus mark. So this is an assignment, or you can say a preparation quiz for you. You have to watch this video, understand this these three slides, and you have to explain me that what is going on in this kind of routing. So let's talk about something that is known as timers in RIP. So you know that this timer is basically something that maintains the time log actually. So you can have three timers in this RIP protocol. The first one is periodic timer, the second one is expiration timer, and the third one is garbage collection timer. So the periodic timer is basically is about 25 to 35 seconds. It updates itself about this period of time. It expires the information of a specific node or device if it hasn't heard about it in 180 seconds. So this is very much good. If you have a routing table, you are maintaining a table, and you have a device that is there was some time before. Let's say there was a device X, and it was there at let's say 5 hops, and you haven't heard about this X again, let's say after 180 seconds. So this router R1 will expire this entry after this 180 seconds. Similarly, there is another time of garbage collection section. This At this time you can see that I have already explained it over here. When a router becomes invalid, the router does not immediately purge the route to its table. It continues to advertise the route with the metric of 16. So you can see that the maximum hop count for this protocol is basically 16. You can have up to 16 hops. The cost that we discussed in the previous slides is basically 16. This is a maximum hop count that you can have up to in this routing table. So not bigger than 16 hops you are allowed to put in this kind of protocol. So let's talk about some of the problems that is in RIP. It has a slow convergence, and what is slow convergence and stability? Let's talk about that. Change somewhere in the internet propagates very slowly through the rest of the internet. So if there is sudden change in some kind of network in the, far away from you, so you will not be able to understand or know about it very quickly. It will take some time to you for you to know that there is some change in some kind of networks. For example, it will take much time if one of the server of the YouTube is gone down, so you will have to wait some time after it gets they get the router updated or the data center updated. So it will take some time. So the first one is this is slow convergence. You will not be able to know about different devices that is coming and leaving your network suddenly or instantaneously. So the it has that much of you can say disadvantage. And to limit this, basically you have applied alternate solution, and that is to limit the hop count up to 15. So router will be there to manage. If let's say there was a device and it was connected to yourself, let's say at 150. So let's say if after some time this 150 becomes 147, so you will not be able to understand that which device inside has gone or which device is down during this time. So to cope that solution, you have limit your thing up to 15 hops, not 16. Now it is up to 15. So thus an autonomous solution for a system for using this protocol is limited to a diameter of 15, and the number 16 is considered infinitely. So if you have a router that is or a device that is connected to you using, let's say, 16 hops, so this is will be considered as infinity. You will not be using it. You will search for something less than 16, that is maximum 15. So this is the good way to limit your basically network. You can see that the total hop count should be less than 16. Now, what is instability? Instability is a kind of a phenomena when a protocol or internet running that can become unstable. A packet could go from one router to another router in a loop. It will continuously go to one to another, and it will keep bouncing back and forth between two routers. So it will cause the instability, or you can see the congestion or network overhead. You can call it as many terms. You can also call it load. So you are just increasing the load, hence you are causing the instability towards your network. So that's all for today. I hope to see you in the class as well, and I look forward to your questions, because you know that the more you ask, the more you learn. I'll see you in the second lecture with the topic of OSPF and BGP. Thank you. Allah Hafiz.